Hi all. I'm sure you can appreciate how frustrating this is for me as well. I'm very sorry that I'm kind of having to do the lesson this way around. I'm not really sure what's happened with Teams. I've spoken to the IT department and we're going to hopefully get it sorted. In the meantime, what I'm going to do is record a little video. I will stay online to answer any questions about it. Shouldn't necessarily have clicked from beginning, but we'll run through it really quickly. I apologize for this setup where I am filming on my phone a view of my computer screen, which probably doesn't give fantastic picture quality or sound quality, but we'll work with what we have. So this is just two starter questions to find the term polymer. A polymer is a series of repeating subunits called monomers. Draw two units of the polymer PVC. I'm not going to do that right now, but it was in the last lesson that you looked at where we looked at PVC. So I'm just going to talk about a couple of different reactions here. You have the slides, so hopefully you'll be able to read through them, so I'm not just going to read off them. But addition reactions, this way you kind of take two molecules and turn them into one. For example, the one that I've given you here is an example, which is mentioned in the syllabus, is making margarine, the hydrogenation of polyunsaturated oils. Now, polyunsaturated means that there's lots and lots of double bonds in the chain. And what it does is it uses this nickel as a catalyst and adds hydrogens and breaks those double bonds. This causes the oil to turn more like a fat in its properties and be solid at room temperature, but it does give it a really low melting point, which is where you get these kind of nice spreadable margarine-y, can't believe it's not butter things. There is a question about the long-term health effects of these, as to whether or not they're healthier or less healthy than traditional saturated fats and unsaturated fats. I'm just going to flick on to the next slide there. Elimination reactions. This is exactly what it says. One thing gets taken out of a bigger molecule, it gets eliminated from the larger molecule. The example I've given here are dehydration reactions. And the one that you've actually completed yourselves is using aluminium oxide to dehydrate ethanol to make ethene. Once you take the water molecule off that ethanol, you end up with ethene. And the other example I've given here is this molecule where they've used hydrogen chloride to remove a water molecule from it. Again, it's a dehydration reaction. Redox reactions. This is the one I really wanted to talk to you a little bit about and explain, because this is what I would like for you to do over the next few days. I'm going to ask for this to be given back to me by the lesson on Friday. Provided I get all the videos sorted, hopefully we'll be talking about it in person then. But the experiment is kind of explained here. What I want you to do is get some red cabbage, and it can be, you know, like a jarred red cabbage or fresh red cabbage. You stick it in some boiling water for 3 to 5 minutes. You can boil it on the stove, but you actually can just stick it into boiling water. It'll work. I want you to strain the cabbage bits out and keep the purple liquid, which is an indicator. Then I want you to use small glasses or plastic containers and pour like 5 mils, you don't have to be super exact, of hand sanitizer into the 4 containers. You want to do that first, and you want to do that early in the morning. Because what you're going to do is you're going to leave them out for several hours. The first one you're going to do the thing to straight away, and you're going to add a few drops of the indicator to it and record what color change occurs. Then you're going to set the other 3 aside and leave them. 3 hours later you're going to come back and do the same thing to the second one, then to the third one, and then to the fourth one, a total of 9 hours later. I'd just like for you to record what color changes you see, and then I'd like for you to write this up as just a bit of an experiment. I'd like for you to include what we call a null hypothesis. That's where, when you plan an experiment, you often say like, oh, I think something's going to happen. And for some reason, when you actually go to do these experiments at uni, they ask you to write what's called a null hypothesis, which is the opposite of what you think is going to happen. I'd like for you to include a null hypothesis in your experiment. You can Google it and get a little bit more information about it. I'd like for you to write up your method. You can just copy mine out. do a diagram of your apparatus, results, and conclusion. I'd like for you to say what reaction you think has occurred between the hand sanitizer and the air over time. I'd like for you to draw the reaction. It is going to be a redox reaction, so that's a reduction oxidation reaction. So that's usually when we talk about organics between alcohols, aldehydes, ketones, and carboxylic acids. If you have any questions about that, please email me, because I would really like for you to do this, and I'm really interested to see the result. I actually wasn't able to complete it myself because my red cabbage disappeared. So I'm really interested to see results. Did it change at all? Did it not change? And see if it works with something with such a high percentage alcohol in it. Breathalyzers, this is just something to talk about here. Pre-digital breathalyzers use the reaction between oxidizing agents and alcohol in the breath. Potassium dichromate, which is this little orangey crystal stuff. I think you'll use it in one of the experiments. In the organic section, it turns from orange to green as it reduces, as you go into the different oxidation levels of the chromium. Right, organic compounds which can act as acids. I'm sorry I'm flying through this, but I want to keep the video kind of short so I can upload it and get it to you. So when we talk about organic compounds that can act as acids, we are generally referring to two groups at the leaving cert: alcohols and carboxylic acids. So they might also act as bases under certain circumstances, alcohols, but I would like for you to think about the Bronsted-Lowry acid-base definition, where a proton receiver is a base and a proton donator is an acid. So in the case of an alcohol, it can donate the alcohol, and we're going to talk about that in just a second. So alcohols will only act as acids with very reactive metals such as sodium. Right, so if you look at this reaction here, you've got the ethanol and sodium. Because the sodium is so reactive, what it does is it pulls this hydrogen off it to make sodium ethoxide and hydrogen. So it's donated those protons, but it just forms hydrogen gas in this case, in this half equation. And that will bond onto the electrons from the sodium, which the sodium is really trying to get rid of. It won't actually act as an acid if you add things like sodium hydroxide to it. It'll only react with alkali metals. So you're looking at sodium and lower in that group 1. Right, the carboxylic group. I want to talk about this and really talk about the carboxylate ion. So, sorry, that's because I tapped the table again and I am balancing my phone so that it can look at the screen. Now the carboxylate ion, this is where you've got your carboxylic functional group here, which is made up of your OH and this C double bond O. Now because this carbon here has got a slightly positive charge on it, it causes the electron which is loose in this OH minus group here to shift towards the carbon slightly, giving a temporary dipole between the oxygen and the hydrogen, which is why the carboxylic acid group really wants to get rid of that proton. If you think back to the Bronsted-Lowry definition of an acid, because of this induced dipole kind of situation, again, remember the induced dipole from when we were talking about the bromine and ethene reaction. So this proton bounces off here and you end up with this O, and that's got a negative charge to it, and your double bond O here. But what's been shown using X-rays is that that double bond kind of flicks back and forth between the two oxygens, giving a relative stability to this new carboxylate ion, as opposed to the carboxyl group. Sorry, I think I said carboxylate group earlier, but I meant to say carboxyl group. The carboxyl group in the carboxylic acid loses a hydrogen and becomes the carboxylate ion. It's a fairly stable ion. Right, that's what I wanted to do about the carboxyl. Right, and next lesson we'll be talking about organic synthesis if you want to have a look up at it in advance. I'm going to end this video here. I apologize for it being a really quick video. I'm trying to record it whilst the lesson's still going on so that I can get it to you before the end of today's lesson. I hope you're all well, and I hope to see you soon. Bye.